In this video, we'll be looking at semiconductors, and in particular the semiconductor diode. From our periodic table of elements, which you might remember from your chemistry days at school, we're going to be looking at this group of elements. And they are arranged in such a way that all the elements in this column here have 4 electrons in their outer shell. This column has 3, and this column has 5. Looking at this basic model of an atom, the outer shell is called the valence shell, and electrons in this outer shell are called valence electrons. And different atoms have different number of electrons in their valence shell, which is how they react differently in certain situations, or why they react differently. So if we take a slightly closer look here, you'll probably be aware that silicon in particular is our element that we use mainly for, or almost exclusively these days, for as a semiconductor. We also do use germanium, but not very often these days. And associated with that, we use a couple of other elements, boron and gallium on this side, and arsenic and antimony on this side. Now, a piece of pure silicon arranges itself in what's called a crystal lattice structure, and it has very, very strong bonds. And the way it does that is that this atom, for example, has 4 electrons in its valence shell. Now it wants 8, because 8 electrons in a valence shell makes an atom very, very stable, and that's what all atoms like to do. So this atom talks to its neighbors and says to them, I'll share an electron with you if you share an electron with me, and so on, with all of its neighbors. So it effectively ends up with 8 electrons around it, which it sees as its own electrons, so it feels very stable. This atom does exactly the same with all of its neighbors and so on through the material. So the atoms, when they share valence electrons, they form what's called a covalent bond, and it creates a very, very stable structure. And it's so stable that not only will it not take part in any chemical reactions, but it also, we can't get current to flow through it because it won't release any of the electrons, and so it becomes effectively an insulator, which isn't much good to us as a semiconductor. So what we need to do is we need to introduce an atom or a certain number of atoms, somewhere between 5 and 10% of atoms that have a different atomic structure to them. And when we do this, we say that this is called doping. And as an example, if we dope our material with arsenic, arsenic has got 5 valence electrons. Therefore, we call it a pentavalent impurity. Now, 4 electrons will take part in covalent bonding with its neighbors, and it is left with a surplus electron. So it will get rid of that surplus electron, or allow it to go free, and it will wander through the material and can then take part in current flow. And because we have now an excess of negative charges, if you like, we say that this material is an N-type semiconductor, because it has an excess of negative charges. If, on the other hand, we dope our material with something like gallium, which has got 3 valence electrons, we call this a trivalent impurity, and it ends up with a hole in the covalent bond that's able to accept electrons. So an electron from this atom may jump across and fill in that hole, and the hole would then migrate around our piece of material. And because this hole acts effectively like a positive charge, because it accepts electrons, we say that this type of material is a P-type semiconductor. Now, when we bring a piece of P-type material and a piece of N-type material together, we create a P-N junction. and there's a barrier here. And what happens when we bring these together? Electrons on the N-type see the holes on the P-type, and they migrate towards the junction, and they're able to cross the junction, and they create a depletion layer, or an area that's depleted of electrons and holes. And as this grows, it gets to a point where electrons can no longer be attracted by the holes because of the distance, right? And so internal current stops flowing. And this is called the depletion layer, or the depletion region, because it's depleted of holes and electrons. If, however, we attach an external EMF to our PN junction, so that the negative is against the N-type of the material and the positive is against the P-type of the material, the negative repels the electrons towards the junction, the positive repels the holes towards the junction, decreasing the size of the depletion region, allowing electrons and holes to combine here, and so we have current will be now flowing in our semiconductor and in our external circuit. When this happens, we say that our PN junction is forward biased. If, however, we connect our external EMF so that the positive is against the N-type semiconductor region and the negative of our external EMF is against the P-type, the holes are attracted away from the junction, the electrons are attracted away from the junction, so we end up increasing the size of the depletion region, and so no current will flow across the depletion region or the junction anymore, and so no current will flow in the external circuit, and we say that in this particular case our PN junction is reverse biased. The symbol for the diode is an arrow against a bar, and if we imagine that, or we say that the bar end of our diode is what's called the cathode, and the way we remember it's the cathode, if you remember, look at the bar and these two parts of the arrow, they sort of look like a K. So this is the cathode end. The other end of our diode is the anode, called the anode, and current flows in the direction of the arrow. However, this is this is conventional current flowing in the direction of the arrow, because diodes actually were invented before semiconductors, when we had thermonic valves. And back then it was thought that current flowed from positive to negative. So the arrow in semiconductors always points in the direction of conventional current flow. All diodes will have a bar on one end, or some sort of a marking like this, and the bar, or the marking, the band around it, equates to the bar on the diode. So the band around our diode in this particular case is the cathode end of our diode. Over here we have a couple of more diodes. They are encapsulated in black plastic, and they normally have a silver band around them showing the cathode end. This type of diode, which is called a single signal diode, normally has a red band around it. This type of diode is a high current diode. It's able to be bolted to a piece of metal to keep it cool, and it will have a symbol on it showing which end is which. There are various different types of diodes, and they all have slightly different symbols, and we'll only be looking at a couple of them in particular as we go through. However, first of all, we want to look at what's called the diode characteristic, or the current characteristic curve of a diode. If we forward bias a diode and start increasing the voltage, the forward voltage from 0, no current will flow until current starts to flow a little bit, and then all of a sudden we get what appears to be no restriction in our current flow. And for a silicon diode, this happens at around about 0.7 of a volt, normally somewhere between 0.6 and 0.7 it starts turning on, and at about 0.7 it's fully turned on. For a germanium diode, that voltage is about 0.3, but we won't be looking at any germanium diodes or mentioning them again. So what happens at this forward when the diode turns on, the current is then limited by the resistance in the external circuit, and we have to have a certain amount of resistance so that we don't have too much current flow, which would cause our diode to heat up and destroy itself. If we put the external voltage in the reverse direction and we reverse bias our diode, we do get a small amount of current flow. It's called leakage current, and it's often down in the 1 or 2 microamps. And for most multimeters, it's at so low that we can barely, if ever, measure it. So for all intents and purposes, we say there's no current flow. And this will continue until we reach a point where the voltage, the reverse voltage, is so high that it will force the electrons and holes across the junction. But when this happens, we end up destroying our diode. So we have a maximum that we can, maximum reverse voltage that we can have across our diode, and we call that the peak inverse voltage, also known sometimes as the breakdown or breakover voltage. But for general purpose diodes, or for just about every type of diode except 1 or 2, that will destroy the diode, so we never want to get to that particular point. Here is an image of a data sheet for a diode, and this particular one is for the type of diodes called 1N400 something or other, 1 to 4007. When we see a number like this, 1N something or other, that tells us that it's got one PN junction, and this relates to the other characteristics of the device. So 1N tells us it's a diode. Not all diodes have a number 1N, they have different ones, but this particular type of diode does. Here is our range from 1N4001 to 4007. And we can see that the breakover voltage varies for each one, but the other characteristics are the same. So they are all able to handle 1 amp, for example, which is what we're particularly interested in. So if we were using this type of diode on a small voltage, like a 12 or 24 volt circuit, up to that, we can use the 1N4001. But if we wanted to use a diode on mains voltage on 240 volts, or up to 400 volts peak, we would in fact definitely want to be using a 4005 to 4007, somewhere around one of those 3 diodes, because it can handle the reverse voltage. Whereas if it's a low voltage, we can use these ones. However, we could use a 1N4007 on a low voltage circuit. It wouldn't make any difference, because the other characteristics are the same. Where do we use diodes? We do use them as light-emitting diodes, and we'll be looking at that shortly, how they work. We also use them in a circuit called a rectifier circuit, where we turn AC into DC, or in any particular case we want to protect a circuit against reverse voltage and reverse current. We can use them there. There's another type of diode called a Zener diode, which we'll be looking at in this course a little bit later on, and we use that when we want to regulate voltage. There are other diodes called photodiodes, where they convert light into current, or light turns them on. We won't be looking at those in this particular course, except to mention them here. And also for signal diodes, which are normally used in high frequency circuits like radio circuits. They're very, very low current devices. And once again, we won't be talking about those except here, and we won't be mentioning them again. So that's a brief overview of diodes and how they work. And the next lesson, we'll be looking at how we use diodes. In particular, I think the next one is we're looking at light emitting diodes, and then we'll look at the rectifier diode.